So welcome to demonstration to video 2 in our course G05 Antibody Analysis. Here we're looking at motif identification. So motif is a short variable region of some sort of sequence, protein, RNA, DNA, and we want to infer the consensus based on an input set of sequences. So we're looking at a position weight matrix, PWM, which is also called a POSSUM position-specific scoring matrix or a position-specific weight matrix as well. So what we want to do to get to the end is get this sequence logo containing the information content across these different sites that are present. Note for the calculations for this contain a few steps, but we're essentially looking at the frequency of each base at each site, and we're counting up the number of bases at each site. We have to use a pseudocount function to input to modify our rates if there's low values present. But essentially, we have your counts and the number of sites that are present to get the frequency of each base at each site I that is of interest. We adjust this by the background rate, which is across all sites I, to get the position weight matrix value, which is the value for B at I, and it's log to scale based on the value for that site by the background rate. And then we're able to get the information content from that by taking the log2 of the rate of B at I, multiply the values across B as well, scaled by a constant 2. So to implement this, we can use tools from the meme suite, principally meme, the multiple exploitation maximization for motif elicitations, and then also this other tool called GLAM2, global gapped local environment of motifs version 2. And the latter is especially of interest to look at discontinuous motifs, ones that maybe have structures that are more complex, and this is generally more effective. So what we're going to do is firstly install the meme suite of tools, and then we're going to decompress that, go to the folder, ensure that it's built properly, which may take some effort, especially when you need to export your path, the locations where you installed it appropriately. Note that you need to change U here, the U part, to your own directory. And then we'll make to install it, make test it, and make install. So those will take a while. We're then going to go to your executables are at bin, which will be in your path. And from there, you should be able to execute the command meme to look at, say, those BOS sequences we talked about before and send our output to a folder BOS. And then look at that output to look at the meme.txt file to do a tabular version of our output. And then also look at the PNG file to look at the sequence logo that's produced. So expect to get something like this, where we have this table containing our input data and then our consensus sequence logo at the end looking something like this. So you can see the number of bits present for the different amino acids, and you see that we have some regions that are more challenging to infer what the most likely amino acid is. GLAM2 is similar to meme and produces similar results. It allows indels, which is very, very useful. It uses a simulated annealing algorithm using varied temperatures to optimize our alignment after starting with a random one at the start. So this kind of makes many changes to the initial alignment to estimate which ones are the most likely outcome. And it's rerun for a number of times. 10 times is typical to see if the motif created is the best scoring one, and that is repeated if the score is not high. Of course, if we have many sequences, maybe we need to rerun many times to find the optimal global alignment if that's of interest. So an example is given here where if GLAM2, our output is sent to BOS2, we're putting P for protein, note that, and then BOS.fa at the end. So what we can do then is go to the folder. We can use Google.Chrome to look at the HTML file, and that will give us a table like this. I can scroll down the table containing our consensus, our sequences that give us a consensus sequence to find the actual sequence logo, which is the logo with SSSE file And we see our sequence logo there. Only it's the same as the other one, but you can see there if there's any differences there. And when you eventually look across, you'll find that there's a slight difference for the final amino acid here. That's the only real difference, at least that I can see. So let's now go to the server. Okay, so we first need to download the meme suite of tools. So to do that, we're using wget to download it from this website. You can see it's downloaded as a tar.gz file. You can see that it's large, so it'll take a while to download. What we're going to do next is use the tar xvf command on this gzip file to decompress it, unzip it, and decompress it to create a folder called meme-version 5.5.3, and then we go into that folder. So we decompress it and go into that folder, and then we can configure our path. So what we're doing in this command above, just shown, I scroll up to it, is we're setting a prefix to the home/meme as the place in which we want to run this program. And we're just executing the commands that are required here. One of these is to export add meme to our path. As you can see there, we've got the path to put MNT, Luster, RDS Live down in meme bin, and the same the lib exec one as well. So we add that to our path, and we can check then that it's in our path, doing check echo $path. You can see that's added on there. We've got meme added there, so that's good. So now we can execute meme from wherever we need to execute it. So what we're going to do is copy over a file .test.fa from our lower directory folder to this place. We're going to meme and we're going to give it the test.fa input, and then we're going to go -out, -o for out. We're going to call it test. So there's a slight error there. Let's actually use the bos.fa files from the folder below, and we're going to meme dash with bos.fa as input -o, and let's call it bos as output. That's running now, which you can see. The issue with the previous one is that you get a single file. What we can do then is go to our directory, go to where we are here, go to the BOS folder. And if we look at the file, we've got logo1, which appears as a sequence logo here. Now it should there appear. So we have our sequence logo present, and you see that it matches the pattern we expected. And that's from the 65 positor sequences that we had as input. We also have a meme.txt file. And if we open that, we can see that contains the kind of table of the VDJ alignments that we have. So you can look at ones like this one that is quite somewhat longer. This one here, and we can look at other parameters for running it as well if that's of interest. So then we have our GLAM2 as well. So GLAM2 has a similar arrangement. The one difference with GLAM2 is that we should note that its input, the output file goes first. So BOS, we're going to call it just GLAM2, and then our input file, we put in our P for protein, and then our input is bos.fa, and we let that run, and it's writing that directory to GLAM2. And what you see is that it's going through 10 iterations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, to optimize the alignment for this set of sequences. So what we can do is actually go to that GLAM2 folder, and we'll see our data is stored here in GLAM2, and what we'll do is open up the HTML file to view that then. So if we refresh that file, we now see that our different results are producing, including the glam2.html file. So what we're going to use is Google Chrome to open that file. And what we can see there is that's produced. Oh, maybe not quite. We have to go into that folder and then run it. That makes more sense. And what we're going to do, what we need to do is just remove this space here, and So what we can see if we zoom in a little bit is the alignment for each of our input sequences. You can see that they all have comparable lengths and they have different scores depending on how similar their alignment is to the consensus one. So the slight anomaly for this one here that's a bit longer. And then we see our consensus sequence logo here, which is similar to what we had with meme. We can optimize that alignment further using LAMP2, such as taking this option to rerun with the maximum number of iterations without improvement to find it. And there's other things we can do to improve this sequence logo. But this is the basics how it can run, and bring along your data to the lab where we can test that further.